Well, thanks everybody for joining. Again, I'm joined by a bunch of empty chairs here in the conference room. So me and a pack of cookies is it. Again, if you want to join, you're welcome to, and there'll be some cookies here. If there's something else you would like, maybe feel free to let me know what would be a better lure to make it up here to the sixth floor. But without further ado, thanks for welcome back everybody from after spring break, which was also fun because we got to do daylight savings time right towards the end of that. And then here in Blacksburg, it turned to frigid Iceland type thing where we had lots of snow flying in the air. Much of it stuck yesterday, but it was pretty nice to look at. But for today, we have Dr. Xueling Dr. Xueling Shi, who is with my group here at Space VT, the Super Garden HF Radar Group, and she will be talking to us today about some things relating to ULF waves. So without further ado, Xueling, feel free to take it away.
Thank you, Kevin, for the nice introduction. Can you all see my screen? Yes, good. Let me just full screen. Good so far?
Mm-hmm.
Yeah. Thank you for the this opportunity to share with you about my research. Let me see, there's a chat over here. Oh, okay. Even though I work for Virginia Tech, but I work remotely in Boulder, Colorado. So that's why I'm presenting over Zoom today. But I do hope in the near future I can visit and make that kind of presentation in person and meet with all of you. But I did my PhD in Virginia Tech as well, so I think I know most of you, or probably met you in person before. So before starting, just want to acknowledge my collaborators. There are so many of them, so I didn't list all of them from here, and some of them from Virginia Tech locally, and Space Science Institute in Boulder, and USGS also in Golden, Colorado here. So that's why I have a lot of collaboration in the Boulder area, and through a few other institutions, both locally or across the country. So my topic today is about intense geomagnetic and geoelectric field perturbations driven by magnetospheric ultra-low frequency waves. So here's the outline of my talk today. So I will briefly introduce a few of the terminology. It's like geomagnetic disturbances, geoelectric field, and ultra-low frequency waves. So that we're on the same page, because even though it's space VT, but we all have very focused research areas, so we may not know about the terminology or each other's research. I think this is also why we need such kind of seminar, so that we can bring people together to know more about each other and probably some potential collaboration in the future. And so the study I'm going to present today started with the data set we use in the methodology, and then a statistics study to quantify the characteristics and the sources of the intense geoelectric fields, then show a few examples of the intense geoelectric field driven by magnetospheric ultra-low frequency waves, and then end with a summary of my talk today. So not sure. I saw there would be some students coming, so I prepare some of very basic introductory material or slides. Maybe the students online as well, so I'm not so sure. So I still present as it is now, starting with what is the space weather, because a main motivation concept of this study is kind of how space weather affects like our technological system. So just like weather on Earth, we also have space weather, which highly depends on the solar activity and the interaction of the solar wind erupted from the sun, and the interaction of the solar wind with the Earth's magnetic field, it generates the magnetosphere, and all those kind of dynamics can perturb like the near Earth space, which can influence both the space and ground-based technological systems. So what we are interested for this study is kind of how like the space weather impact of the either like the magnetospheric UF wave, how that can couple to the additional or induced current in some of the technological systems. So yeah, a few terminology so that yeah, you may be familiar when I'm talking about like GICs or GMDs, geomagnetic disturbances, or geoelectric fields. So as I mentioned, like interaction of the solar activity and with the whole Earth's magnetic field, it will generate various phenomena in the Earth's space environment, which can cause space weather impact. One of them is like this geomagnetic disturbance or variations. It can interact with the Earth's conductivity structure, just regarding the whole Earth as a kind of a conductor. It has its own different region have their own resistivity or conductivity, and those all those disturbances you can regard them as kind of EM waves. They penetrate and interact with Earth's the Earth structures, and then that can generate the electric field at Earth's surface. So we call that a geoelectric field. So of this geoelectric field, and then they can drive electrical current when those infrastructure or grounded systems connect with the electric field. So then those electric field again drives geomagnetic induced current, we call it in some of the non-conductors. One of those examples just if those additional electric field kind of acting as a DC this current, sorry, and they can even blow out some of the transformers in a historic extreme event. So it's kind of hazardous to lots of technological systems such as our power grids and the submarine cables and gas or oil pipelines. So that's why we're interested to study this phenomenon. So as you can see here, the like geoelectric field is kind of like a interface or a very important link between the phenomenon in geospace as well as the GICs, like in grounded electricity transmission network. So the main topic or data set we use is from a geoelectric field. So I will talk a little bit more about this parameter and how we can get geoelectric field. So it can be measured directly through like two electric poles, and but that's those kind of measurement is very limited because you need a lot of kind of effort to keep like those measurement or the instrument working properly. So a lot of times, like it's kind of being calculated through this equation. Like you have the magnetic field variation, then you know about the Earth's conductivity structure, which is denoted as the surface impedance here, the Z value here. We can get that through the magnetotelluric surveys. The mention it depends on the Earth's conductivity. So you have this being measured and also the magnetic field being measured, then you can calculate the geoelectric field. So two different ways the geoelectric field can be obtained. So in this study, we are focused on the kind of the direct measurement of the geoelectric field, even though it's pretty limited, but that's such kind of data set over there, and I will introduce that later. So this is kind of one example from one of our previous study from Hunter et al. 2022. I'm also a co-author of this paper. It shows like one of the measured geoelectric fields through a very small array around here, I think close to the which state I cannot remember. And this region, for I'm more familiar with the US maps. But yeah, this is a measured magnetic field as well as the geoelectric field. And also, because through this kind of magnetotelluric survey, you get the information of the surface impedance. Yeah, you can also calculate the electric field. So this just the two comparison. The black line is the actual geoelectric field being measured. The red line is calculated. As you can see, through the comparison of measured and calculated geoelectric field, most of the time they are pretty consistent with each other. So when there's a measurement, we use that. And a lot of the time, when there's a lot of kind of direct geoelectric field measurement, we can can use like this surface impedance, which is Z here, then to calculate in those other kind of dots. When you have a more long-term geomagnetic field monitor data, then you can get the geoelectric field. So here's some examples of how we get a geoelectric field. And also like one of the drivers of those intense geoelectric field is kind of plasma waves in magnetosphere when they propagate to the ground. So here just a kind of introduction of what is plasma wave. So in the whole geospace, there are various wave phenomena, and they are analogous to different musical instruments shown here. And when the sun kind of perturbed the magnetic field, so you see this magnetic field line, just some of them like guitar strings, they evaporate in different directions, and that's what causes the magnetic field perturbations. And so some of those waves are within the human audible ranges, and you can actually hear them. So I will show a few examples of those high frequency waves. You can tell from their names probably how they sound, like whistlers or sound like chorus or hiss. So I hope the audio will work. This is a whistle. And then here's a chorus. Too loud for me. Not sure if you hear it properly. Does everyone hear that? I'm not so sure. Okay, I see. Yeah, Kevin kind of nodding. So yeah, so those are kind of high, very high frequency waves, which we can just hear just about air. But there are also other kind of plasma wave, which we have been talking more about today, kind of ultra low frequency wave. Their frequencies are so low that we cannot not hear them directly. So you need certain techniques or tools to make them audible. So I'm also getting involved in one of the citizen science project. Here's a link here. You can actually through this kind of techniques and actually hear the ultra low frequency wave just as you did hear those VF wave I showed in the last slides. So yeah, but that's not the main topics today. So it's just trying to give a more intuitive kind of a sensing of what a plasma wave or ultra frequency wave there might be sound. So the nature of the ultra low frequency wave we're going to talk about today is kind of EM waves and the frequency of 1 megahertz, very low frequency, to a few hertz. And so they historically been named like geomagnetic pulsations. If you hear about that, like pulsation continuous or irregular, depends on their waveform. The more continuous, a several wave cycle, or more impulsive, just last for a few minutes. And there are also subclasses of those waves. You heard about like PC5 waves or PI2 waves. So I'm not going to too much details of these terminologies. Here's just one example, like even dating back to the last century, like you can see a report of those we call magnetic pulsations or kind of variation in the geomagnetic field, even through the compass needle. So when you have this long period waves, like the needle would be being shifted a little bit so that you can see the records through that. So it has a very long history of the study of those waves, how they've been generated, what's the nature of those waves. And so how those waves being coupled to like geoelectric field and or like the GICs were interested and may cause some trouble in some of the technological system. So those waves, they can be generated through the interaction of the solar wind and the magnetic field, as I showed before, and they can propagate within the magnetosphere, and some of them coupled with directly to the magnetic field line and cause vibrations. And then those waves can propagate all the way to the ionosphere of the ground and being sensed by either the ground-based radars, like the shoot-down radar can sense those waves, or ground magnetometers and cause geomagnetic field perturbations. So we know the geomagnetic field perturbation and can couple to geoelectric field and cause the electric field on the ground. And then the electric field again drive current in the infrastructures. So this is how the ultra low frequency wave can couple to both geoelectric field and the GICs. So for geoelectric field itself, like as I mentioned, it depends on the geology. So the Earth underneath our feet. So in some regions, when you have a low conductivity, and the geoelectric field will be larger. In regions like if it's a high conductor, so you basically have a smaller electric field, and also those current being conducted. It depends on the Earth's conductivity as well as like the properties of the geomagnetic variations, like their frequencies and their amplitude, how strong those. So it's a complex system, how it works. And so the ultra low frequency, as I mentioned, it can couple to magnetic perturbations, and thus the geoelectric field and the GICs. So that's how they're being connected. Here's just one example from a previous publication, show like in some of the region, I think this up Midwest, Michigan Lake regions, and how like the geology like there, and also coupling with different wave period, which is color coded by red, black, and green. Basically, they have synthetic magnetic field perturbation at a sinusoidal wave of different frequency, all within the ultra low frequency ones and of the same amplitude, and see how that are coupled to the geoelectric field, which are these vectors here, and also how the geology and Earth's conductivity, the color coded here, affect the wave amplitude of polarization. So the color coded here is the resistivity, basically the larger values like the red, the blue here, larger value means more resistive regions, as we introduced in last slides. More resistive region where generate a larger geoelectric field. So that's why you see those vectors have a longer amplitude compared with more conductive regions. And also quantitatively, like those kind of red or black lines have a lower have smaller wave cycles, like 10 seconds, 100 seconds, compared with those long period wave. They have relatively larger wave amplitude. And also you can see those vectors, their polarization and directions are different from region to region. That's also due to this surface impedance and because of the geology in those regions are different. So they shifted the magnetic field angles or the polarization different, so that the geoelectric field are different polarized. So what is the motivation of this study? I talk so much about like how the UFO waves and they coupled to geoelectric field and the GIC. That's also have been reported, and one of the study we talk about today is my work published last year. But it's still some issues like because the waves and all those kind of report have a large geoelectric field at GIC, and mostly case study and at a relatively high latitude, like say in the Aurora region, which you expect to see very large perturbations. But if the waves at mid latitude, say within the United States, can drive significant like geoelectric fields? That's still one question. And in fact, that is one of the comments we received from the reviewer. They have highly doubts, like wave usually have relatively smaller amplitude and lower latitude or mid latitude. If that can play an important role, that's a question. And also, the driver of those of UFO compared with other like the substorm or other kind of solar wind drivers, if UFO is important, play an important role and just compare with the other drivers, there's also something lack of comparison from the past work. So that's why we need the current work or the specific work we're going to talk about today. Oh, by the way, so that's the end of the introduction. I think this is kind of an informal seminar. So if you have any question, feel free to stop me. Don't need to wait till the end of the seminar. I don't know if that's how it goes. Kevin, correct me if I'm wrong. But if you have any questions, just feel free to unmute and ask questions.
Yeah, sure. I was a little confused when you did like the impedance of like Z X Y. What do you where are those, where are the X and Y? Like are they just like placed on the map?
Oh, yeah. Sorry. This we mainly talk about the horizontal component of the magnetic electric field. So XY basically you can decompose that into the north south and east west, and just the two component. And so basically you, even for the magnetic field, electric field, we only consider about the horizontal component because they have like decomposed into, it's a vector decomposed into north south and east west component. And these are different components, just probably a representation of the 3D kind of Earth conductivity structure, because they not only have like the horizontal structure of the Earth's conductivity, how the gradient is there. I don't know if that answer your questions.
That did help. Yeah, thank you.
Yeah. Again, if you have any question, feel free to stop me. I know because we, as I mentioned, we all have different from different research areas. So I may not, I'm too familiar with this familiar, so I may not explain it in a more plain language so that you can understand. Just definitely stop me and ask the questions. I can provide more clarification. Thank you. So I will continue with the data set and the methodology, which I will be present as a result. So here, like this map, it shows the data, like or the site, the location of the station we use for this study. Actually, I mentioned like the geoelectric field measurement is very limited, but we do have this NCF supported Earth scope program. It's a magnetotelluric component of the US arrays. Basically, they have like probably a few tens of sites, like where measure the geoelectric and geomagnetic field at the same time for approximately 3 weeks of time intervals, so that you have enough of record being covered at different kind of period. So you have magnetic electric field measurement, then use certain inverse techniques, then you get the Z we mentioned before. Because Z, it depends on the Earth's conductivity, and there's very large geology activities, so it mostly remains stable. So that's how they get the Z we mentioned before. Then after they stay in certain region for a few weeks, then they move to other regions. So it's not a permanent site. It's kind of keep moving so that it have the complete survey of the United States region. And then in the future, if we have permanent magnetic field more data from any of these regions inside United States, so we can use that impedance IEZ to get the geoelectric field estimate. But what we're going to use today is just this actual measurement. It's a 1 second temporal resolution, and it's studied only in one specific local locations of a few weeks. But the advantage of using this data set is that you can take a look at different response at different regions of different conductivities, and even though it's not happen at the same time. By the way, like, so each of those dots is one temporary site, and the kind of spatial resolution and between two of those is about 70 kilometers. And also this is back to 2019. I believe some of those southern part early this year already be completed, and further south, some of this Texas part probably need to be completed in the next couple of years. So here's our the main data set we use is a magnetic and electric field measurement from those scope sites. But if we want to investigate what drives those and the further characteristic of those intense geoelectric field events, we do need some other data set which give us some idea of what the solar wind is doing, and what inside the magnetosphere other kind of geomagnetic activity is doing. So we use some commonly used data set to provide some information on that. And also we specifically, because it's as I mentioned here, the data set across more than 10 years. So yeah, we didn't survey all the sites. We only choose a few like relatively larger geomagnetic storm intervals, which is 16 geomagnetic storm, and based on some of the storm indices, which is less than -100 nanotesla. So this is the storms or period we selected when those Earth scope data are available during this time interval. So in total, we describe the actual methodology in the next slide. But in total, through these 16 storms, we found only six of these 16 storms observe relatively larger geoelectric fields. So then we're focused on the event being identified during these 6 storms. So the actual methodology we use to identify if there's an intense or a relatively large geoelectric field event. So here's the methodology. We use some Python script trying to find the peaks and the valleys. This is in kind of idealized case. We give very sinusoidal wave structure time series to the algorithm. Then it's able to identify the provenance, which is kind of the relative amplitude of a peak or a valley regarding to its surrounding signatures, and also what is the width, with associated with that. So through some trial and error, we do some experiment. We're able to kind of add more constraints so that we can find some of the actual or the physical kind of event, and then remove some of those sparks and noise data, because this measurement is mentioned just a reason there's very limited of this measurement, because you do need, like what I heard, you need people to water in the ground so that the electric field measurement can be more reliable, or also need some probably calibration. But still, it can be affected by a lot of like season, lot of other factors. So it's pretty noisy, as you can see, some spikes or like there, which are artifacts. So that's why we have different criteria so that we can identify as many of those physical events as possible, but remove as much of those spikes as possible. Eventually, after we identify those events, we also plot them, zoom in to take some visual inspection through eyeball to see if any of those are artifacts to us or not, then remove those events. So here, after we've identified those events, then we generate a summary plot like this. This is a bit busy plot. I will walk you through each panel. So the top panels is just what suggests the condition from the solar wind. If we know there's kind of some structure from the solar wind compressing the Earth or in contact with the Earth, and then after that, if we observe some of the intense geoelectric field, which identified by the cross here, this is the Earth scope electric field measurement, and this is the corresponding magnetic field perturbations. And this is some indices, aurora electrogen indices, and the symmetric, similar with the DST indices, suggesting if there's any substorm activity going on, or if there's any storm activity going on. So like these are 2 examples, like from at the very beginning of the storm, you see enhanced in this indices, and also some independent structure coming on. This is kind of the initial response of the whole geospace according to a kind of a shock structure from the solar wind. And afterwards, you do see during some other intervals, that very intense geoelectric field being observed. There's some other structure also in the solar wind, like it's kind of the independent magnetic field kind of rotating its kind of direction, and also some the pressure from the solar wind also changed. So that's probably another abrupt change from the solar wind, and then cause a whole magnetosphere as the waves and other structures being changed, and then cause the ground perturbation. So here just one example show you how we identify different sources what drives those intense geoelectric field events. Here's give you a little bit of statistic of how many events we've been identified. As I mentioned, we surveyed through 16 storms, but only 6 of them we found those kind of actual intense geoelectric field events. And they are all from 24 of the Earth scope site we mentioned. And in total, there's 361 intense geoelectric field, we call that event or the peaks being identified. And also we take a look at like the width, like I believe it's a 4.5 maximum of those peaks, and also like the prominence, which is kind of relative amplitude of each peaks. So let's take a look at the property of that, and then we So the y-axis here is the width, and the x-axis here is the prominence. And we separate them by two horizontal components, like the Ex is the north-south component of electric field, and Ey is the east-west component of the electric field. And so really, like different community have different threshold, but here, like if we talk about 1 or 2 volts per kilometers amplitude of geoelectric field, that's kind of already pretty large in our community. Even though from some people in industry, they think like you need to go through above like 8 or even higher volt per kilometers in order to have they need to worry about their infrastructures or system. And so we try to identify like the lower bound, like if the prominence greater than 0.5 volt per kilometer, what is the possible driver of those events? So a few takeaway message here, since we're using 1 second resolution data, so the width information tell us that the majority of those events, their widths are kind of less than 1 minute or 16 seconds. The reason I want to bring out this 1 minute is because in our community, lots of people use like 1 minute resolution data because of not a practical reason, or if you want to survey like 100-year events, and so the database too large, so kind of a low resolution, kind of have the statistical analysis, or maybe they think it's enough using 1 minute data to characterize those kind of extreme event. But I will take one message here, like in order to have the more accurate characteristic of those events, you do need a high temporal resolution, because not all those pretty large event we identified, they're like the whole width of those peaks or those events, it's kind of tens of seconds, it's less than 1 minute resolution. If we use 1 minute data, you're not able to characterize those very impulsive events or those wave structures. And yeah, here's just one example of the intense event we identified, and it's associated at least partially with ultra low frequency waves. So the animation here, the black line is the magnetic field vectors being observed by a few of the Earth scope sites during these intervals, and the red line is the electric field measurement. And on the right hand side, it's the same a summary plot we showed before, but we zoomed into a specific interval, which we know like there's a interplanetary shock coming from the solar wind, and right before that, and then following that, we starting to observe like electric field perturbation and magnetic field perturbations. You can just, these are raw data, I didn't do any detraining or signal processing. Just take a look at this raw data, you can immediately see that's very impulsive kind of geomagnetic geoelectric field disturbance being observed right after aftershock. Then following that, you do see some wave signature in both magnetic and electric field data. So that's why I identify these two drivers is associated with like the very transient and very current generated by the IP shock, and then the UF wave also generated by the IP shock. But it's kind of two different mechanism here which drive these two different peaks here. And you can see how the vectors of the magnetic and electric field, they shifted at the very beginning, very large, that's due to this impulse, and then later on, it's due to this kind of waves. So looks like the magnetic field or the wave structure later on is pretty kind of uniform, you can see. But in other events, that is not the case. If we, sorry. Take a look at the second event, which is on the second day. It's driven by like the interplanet magnetic field turning. It's mainly from the BZ southward interplanet magnetic field towards a more eastward, a positive BY magnetic field. And then after that, you start to see not all like UF wave signatures in the magnetic in geoelectric field, and also the magnetic field is not as clear here, since it have a large kind of baseline value which are not subtracting. Later on, I show a detailed case study in this event, since it's very geometric, and both the black line here, which is the magnetic field, as I mentioned, them pretty close with each other, kind of 70 kilometers away. But both the magnetic and the electric field, their response are dramatically different. There's a reason for that, which I will explain later on in a more detailed case study. Yeah, here just more examples of those intense electric fields driven by UF waves. They mentioned some of them called geomagnetic pulsations because you see not all pulsation structures, and this is kind of a longer time interval, a few hours. If we zoom into a specific interval, you do see not all wave signatures there. So just yeah, the last example, just different waveform, different wave period occurred at different phases of the geomagnetic storm. They are all linked with UF waves. So that's the main takeaway message. So for this one, the special about this one, like it have relatively longer period. I think it's kind of 20 or 30 minutes also. So you identify multiple peaks and over a few hours interval. So compared with other mechanisms, like you have very impulsive or kind of short duration of the wave. So this long period long duration you have wave structure, they have sustained peak values. So they may have a relatively stronger impact on those infrastructures compared with those very impulsive, probably 1-2 minute, but relatively larger amplitude event. So here, like, is a summary. Let me take a look how many time I have. Okay, yeah, I still have 20 minutes to go. Good. So here's a summary of like possible drivers. So we take a look at all those peaks, individual events, and trying to summarize them if they're being observed right after IP shock associated with at the very beginning of the storm, and if there are any other conditions like we identify like the MF turnings, or if they observe mostly during nighttime time associated with the substorm activity from the magnetotail, and or if there's any like sinusoidal wave signature being observed and a few wave cycles, and others which we are not able to identify it, if we're not need a kind of further analysis taking into account of other space or ground instruments. So this is just one to quantitatively identify like if your wave is one of the major roles of drive those intense electric field. I think indeed we find a lot of cases the wave is kind of the a very common driver of the intense geoelectric field. And in some of the storms, this is one example of the 2017 May 28th storm. It's in fact the only drivers. We only identify, like during the epishock interval, we don't observe the a very large geoelectric field and a substorm interval. No, so only during the UF wave interval, which is the example we show here. Only during this interval, we observe a strong intense geoelectric field. So we think at least the UF wave we don't know how to quantify it yet because, as we presented before, a lot of these mechanisms they occur simultaneously. But at least for wave itself, I think it's playing an important role of driving those intense geoelectric fields. Here's just to take into account of another very important factor as well, which is the geology or the Earth's conductivity. So if we take a look at the map, this is a kind of, I cannot remember, probably 100, more than 100 kind of Earth scope sites, which we surveyed in total during those 16 geomagnetic storms. And here's like showing like the blue region shows the more resistive region, and red shows the more conductive region. And here's just the distribution of those sites actually observe the intense geoelectric field. So you can see like they are mostly at those blue regions, which are the resistive regions, and also at a relatively higher latitude. So this is a takeaway message, like those intense electric field. It depends on the Earth's conductivity because the more resistive regions tend to have those dry intense electric field. And as well as the source, like including the waves or other kind of MI current, because the source tend to coming from the higher latitude, let's say the aurora region, and during storm time when they expand more equatable, then they'll be able to observe by those kind of a little bit upper Midwest resistive region. So it's kind of as I mentioned, it's a complex system. It needs a geology information as well as what's the driver from the geospace. Yeah, so what I presented so far is from one of the paper already been published last year, just trying to quantify statistically like the overall drivers, including UIF waves of the intense geoelectric field. But if we actually want to identify the exactly driving mechanism all the way tracing from the solar wind and the sun towards the ground, we need all kinds of other instruments to help us doing that. So that is the work I've been doing in the past almost a year or so. We really need to wrap up this study. Just show you to see if there's any feedback or comments here. So there was I showed this before. There's one specific kind of event. I think it's probably one of the largest intense the geoelectric field event we observed during the previous strategic study. And again, it's observed in the Minnesota region of Midwest, a resistant region, and it's observed right after an MF turning. The good thing about this event, we're able to have like a few spacecraft all the way like inside the solar wind and close to the magnetopoles, the boundary between the solar wind and the inner magnetosphere, and also in satellite inside the magnetosphere, as well as like the Earth scope site on the ground, and also like a few sky images nearby, so that we can trace or take a look at the event all the way from the solar wind and then interact with the Earth's magnetosphere, and how that propagate all the way down to the ground and then be observed by the ground-based instrument. By the way, so all the instruments are satellite here inside on the ground around the dusk side region. So if we take a look at the semi-C satellite in the upstream, you do see this MF10 signature. This, by the way, this is different from the previous showing from the Omni data. Omni data basically take into like the Air1, a few other spacecraft, then propagate through certain techniques through the bow shock region. But there's some uncertainties or it's a combination of different spacecraft measurement. So it's better we just take a look at a little bit closer upstream here, the same sea cycle, which directly measure also the similar MF10 being observed, and have a high temporal resolution. And you can clearly take see that's also an impulse solar wind dynamics dynamic pressure structure associated with this MF turning, which might be the driver of the wave as well. And for the semi-E satellite, this is also the magnetic field and the dynamic pressure of the semi-E. It previously inside the magnetic sheet, which is a boundary of the region between the magnetic poles and the bow shock. And then after this structure arrives, it's being moved to the solar wind. Basically, it has something coming from the solar wind, then move the boundary of the magnetosphere. Then the satellite being shifted towards the other region. So you can clearly see this shifting. And then for the GOES satellites, a geosynchronous satellite inside the magnetosphere, you also see some perturbations from two of the GOES satellites around the dusk region. And then towards the ground, excuse me. Then you have the Earth scope site immediately after that, observe the perturbation in both the geoelectric field and the geomagnetic field data. Sorry, I need to take a water break. So with all this data, spacecraft and the various regions, as well as the ground-based instruments, so we're able to kind of take a more detailed look at this event. So this is again just a little bit of zoom in from the previous one, and only show the upstream solar wind observation and two of the Earth scope site, and with some dashed lines, so that hopefully you can see some peaks and valleys of wave signatures from two of the Earth scope sites. So take away message here that you do see this kind of wave signatures, 1, 2, 3 peaks in electric field and magnetic field data. And by the way, this time I kind of detrended the baseline value so that I can put the different component in one panel. And as you can see, these two sides mentioned, they are pretty close with each other. if we take a look at the magnetic field perturbation, they are pretty different from each other. You see a negative bay in both north, south, and east, west component, and you see a positive and then a negative gap in another nearby side. So, and also the electric field response are very different. For this side, you mostly just see the high frequency, like the UF wave response in geoelectric field data. But in this side, you see both like the wave as well as this kind of large base, this longer period perturbations. So basically, you have kind of two mechanisms going on. One is a short period wave, about 1 minute. One is kind of longer period perturbation from magnetic field, which might be driven by some other mechanism we'll talk about later on. So yeah, in total, we have each side also still in the same regions, because this Minnesota region is have pretty old rocks, very resistive, which will have relatively larger geoelectric field or hazardous geoelectric field, and GS is being generated in that region, unfortunately. And so 4 of those observed, and the intense geoelectric field. And so this is a few snapshot, and the right hand side is the animation. Again, black is the magnetic field perturbation, red is the geoelectric field. So you can see in this case, both the black line and the red lines, they are all kind of different amplitude and different polarization, and so because of like multiple driving mechanism occurring at the same time, and also it's pretty intense event. Yeah, so this is just to take a look, because what actually drives are not like the perturbation is kind of overhead in the ionosphere. So we fortunately have kind of a few all sky images, a little bit of west and north of the Earth scope side, and to see if they observe any kind of atmospheric current structures related to auroras, and can drive these perturbations. So we indeed found, like at the same time, which is that line here, when we observe intense geoelectric field, there's auroral activity right going on, like through this side pinna, which is the closest one towards the electric field movement. So you see how the aurora arcs kind of appears at the same time, and then it propagates westward, and then and toward a little polarward toward the north region of the given images. So this is just we also have other techniques using other kind of ground magnetometer in this region to have a sense of the localized atmospheric structure going on overhead. So I didn't show that slide, but it's all confirmed that probably this very localized aurora arc structure is, under the time scale, it's about 10 to 20 minutes, is the driver of those longer period perturbations. And also the wave kind of superposed onto those auroral arcs or atmospheric structures together with this atmospheric current system drive the intense geoelectric field. So to summarize, through a detailed case study and statistical studies, we able to confirm like the UF wave is one of the most common sources driving intense geoelectric fields during storm intervals, which can cause harm to the infrastructures, including power grid. And also like because the dependence of those geoelectric fields on multiple factors, which you need to consider about like the ground conductivity structure, which is different from one side to another, and also the source from the solar wind, the magnetospheric and atmospheric current system, and including like ultra low frequency waves. And in one case study, we able to confirm like the combination of like atmospheric current system related to transient aurora structure as well as ultra low frequency wave, and of course the Earth's conductivity in that regions of bringing together like cause like the relative large intense geoelectric field at 1.5 volt per kilometers out of the Minnesota region. So yeah, that's all I have. If you're interested in more information, that the statistics are presented is already publicly available, and the case study is still in preparation. And some of our previous work link the ultra low frequency wave with geoelectric field or geomagnetic field perturbations. So I'll stop here and see if we have any questions. Let me see. Okay, I got a couple more minutes.
That was great, Xueling.
Thank you, Kevin.
No problem. Yeah, any questions here? So we had a few kind of in the middle there. Yeah, it's certainly kind of informal. That don't have to use that format all anytime.
Well, if I don't hear a question coming, maybe I'll ask. I have access to Xueling and I can ask your questions almost anytime. I wonder, is there any sign of resonance effects on this? You're looking at oscillations on field lines. These are undoubtedly closed field lines. They have characteristic resonant frequencies. That's one question. And another is there any evidence of resonance or bandpass filtering in the Earth's response, such that certain frequencies or periods are preferred over others?
Yeah, both are quite possible and probably the reason for all this kind of response. Yeah, so for the field line resonance, yeah, I also highly doubt because of like the period of this kind of location. Yeah, it's quite close to the field line resonance period. So I haven't confirmed or do a detailed analysis of this yet, but it's very possible. Like what being observed in the magnetic field data is kind of the field line resonance because of coupling of course, other kind of upstream or magnetospheric wave signatures. Although I do need to take a look at a few other ground magnetometer data to see how global or how localized those are right after this MF turning. And so, yeah, for the resonance of, I assume you're talking about the transfer function of the kind of the Earth structure, and it may have at different locations, like prefer different, just these two sites, like, because of like, the transfer function surface impedance, like they have a preferred frequency, so that's why like maybe it prefers this frequency range, so the wave signature kind of pop up here, but it does not prefer the longer period, like the 10-minute perturbation, so that's why it's not showing up clearly. But in this side, so I believe if I'm able to pull like then plot like the surface impedance, how that respond at different frequency, because it's also frequency dependent. I believe it probably then will show up the difference between these two sides and why is this kind of short period wave showing up more prominently, and then it's both the wave as well as a longer period perturbation showing the geoelectric field. I think that's that's a role there. But I don't know if I call that the resonance, but I think there's a frequency dependence or response in the Earth's transfer function itself or the conductivity itself.
Yeah, so you're looking at all this variation in the response as a consequence of local transfer characteristics, transfer function characteristics. Well, what's the distance apart of these stations, 35 and 38?
Yeah.
Oh, they're very close.
Yeah, they're pretty close, but I don't know exactly which one is which one, sorry. But yeah, since these two are observed pretty large ones, and 35 and 38 usually apart probably by one or two or three of them. Let me identify, so the large one is, maybe one of these or one of the, anyway, they're pretty close.
Yeah, what I'm comparing to is the typical scale sizes of, pulsations in the magnetosphere, which, it's going to be several hundred kilometers typically. So with the structure that we're seeing here, it's hard to point to the ionosphere and say that's the source of all that variability. It must be in the transfer function in the Earth. Yeah. Okay, thanks, Xueling.
Thank you for the question. Any more questions?
I'm not sure I fully understand it, but you said that the issue with like the Minnesota area was that the rocks were like affecting the spheres, or starting affecting them more. Do you think is that correct? Yeah.
Yes, that's correct. So is it?
Oh, sorry.
Go ahead.
when we say rocks, like, do you think it was a specific mineral or like what makeup of the rock that may have affected it?
Uh, when I say rocks, it's kind of more, more generalized. It's mainly about the kind of the geology there, like different, like the crust or the mantle or different layers of structures underneath our food in the different regions. Like some of them might have a very resistive crust. Or sorry, I'm not a geology expert, but yeah, some of those papers they describe why they have this different kind of like the surface impedance structures. Like in this region, you do see like here in more upper the north regions they're pretty resistive, and in these regions they're pretty conductive, which is depends on the internal Earth's conductivity structure of different material of those rocks or crust or mantle structure underneath. Um, does that answer your question? Just
Yes.
like you would, yeah, you would take a look at. We do study like submarine cable inductions as well. Like we take a look at the water transfer function or the water pretty conductive, but underneath the water, like the sea floor, and then underneath that the crust and the mantle structure, they all different layers. They have different thickness and they have different material resistivity or conductivity different. So all coming together because when your wave of perturbation kind of penetrates through that. So they have different skin depths, so different frequency respond differently. So all due to the structure of the Earth's structure in that different geology region. Does that help?
Yeah, I think so. Thank you.
Any other quick questions? Yeah, Shirley, I was going to ask one, but I think you sort of answered it with both of those questions without kind of going back to it. I think there's a lot of interest in particular this slide and thinking about that.
Yeah.
You know, the transfer function, the z components. That's an interesting thing to think about. You know, right? It's almost like you have to add a comma with a variance on time there as well eventually, that kind of thing. Yeah. Otherwise, without any other questions, yeah, thank you for joining, everybody. And we will see. I don't have a speaker for 2 weeks from now, but we will see everybody in 2 weeks, which I believe, yeah, will be at the very end of the month here. So thanks everybody for joining, and we'll see you in 2 weeks.
Thank you. Bye, everyone.